everyone, welcome to our channel Knowledge Hub. Friends, subscribe to our channel and click the bell icon for the latest update. आज हम लोग कंप्यूटर नेटवर्क की क्लास करने वाले हैं जो कि क्लास नंबर आपका 7 है। ऑलरेडी हम 6 क्लासेस कर चुके हैं जिसमें हमने यूनिट 1 किया है, इंट्रोडक्शन टू कंप्यूटर नेटवर्क, and that is the second unit we had done, we had completed in the last class only, and that is your unit 2, and that is your medium access sub layer as well. And now we'll start in today's class, that is your unit 3, that is your network layer here. And the network layer, first of all, the topic that what you have to understood about the network layer design issues here. So we'll start with that as well. Network layer design issues. First of all, it's a huge request from my side to all of you, please go through with the subscribe button and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. And in the reference towards the network layer design issues here, that the question they can ask you, what are the functions of network layer? So we'll start with the functions of network layer here. Functions of network layer. In the functions of network layer, which is very important because the unit name is only that network layer, three important functions of network layer we have. The first function we have is here, that is path determination. In the path determination, route taken by a packet from the source to destination, routing algorithm used for this. The second we have is just switching. In switching, that move packets from the router's input to appropriate a router output. The third function we have, and the last function as well, that is call setup. In the call setup, that some network architectures require router call setup along path before the data flow. Where on these, the basic function of the network layer is to provide an end-to-end communication capability to the transport layer which lies above it, and network layer is the lowest layer that deals with the end-to-end transmission, where the network layer protocol that are concerned here with the the exchange of the packet of information between in transport layer entities. And a packet is a group of bits that include the data bit plus the source and the destination address as well. The service provided by the network layer to the transport layer is called a network services. The main function of the network is to transfer information among users that are attached to the network, and the transfer of the information in the network will discussed here by drawing a figure as well. And that the information transfer may be of single block of information or a sequence block of information as well. That could be either in the single block of information or it could be a sequence of block of information as well. And the information transfer may be a single block information or a sequence block of information. In a single block of information, block must deliver to the correct destination, and in the sequence of blocks must be received in the right sequence. So the network layer must fulfill the following requirements. Basically, the first requirement what it fulfills is that the services should be independent of network topology, and in the same case that the second is that the network addresses should be made available to the transport with the uniform numbering plan, and the third is that the transport layer should be shielded from the number of the types and the topology and of the router present. So we'll, as I told you about, we will discuss about with a diagram here, so that we'll discuss here. This is T0. This is the representation of T0. Or you can say that T0. This is connected to a network. And this is connected to a, that is your T1, where this is connected to a block where we have is your, that is, this is connected to the network as well. and this is also connected to another one here. Okay, so this is transfer of information. Transfer in information has been transferring like T0 to a network, T1 in a network, and these were coming to a network as well. This is transfer of information. Okay, for the single as well as the sequence of the blocks here. Now we'll discuss that what were the services that are provided by the network layer to transport layer. So that we'll discuss in a detail as well. The services provided through the transport layer. The services provided through the transport layer here. The network layer provides the services to the transport layer at the network layer transport layer interfaces. With the same, the network layer must fulfill the following requirements. The first is that the service should be independent of the network topology. The network addresses should be made available to the transport with a uniform numbering plan, and as well as the transport layer should be shielded from the number and the type of topology of the router present as well. Now we'll discuss the compare datagram and a virtual circuit. With the same reference towards it, the comparison between the virtual circuit and a datagram, that is a subnet. So here we'll go ahead. We'll discuss about it, the difference between that is the virtual circuit and datagram subnet. So in the case the virtual circuit and a datagram, we'll discuss at least minimum 6 differences between them. So the first differences that we'll discuss here is in the reference towards it, the virtual circuit here, that the circuit setup is required, and for the datagram the circuit setup is not required. For the virtual circuit, that each packet contains a short virtual circuit number as address, and the second we have here is in the reference here is in the datagram subnet, that is each packet contains the full source and the destination address. Here in the third, that is your virtual circuit here, in that the route chosen when the virtual circuit is set up, and all the packets follow this route. In the datagram subnet, each packet is round independently. The fourth difference for the virtual circuit we have, in the case of the router failure, all virtual circuit that passes through the router are terminated, and for the datagram subnet, only crashed packets lost here. The fifth is your virtual circuit. The congestion control is easy using buffers, and here that is the difficult congestion control. The sixth difference is that the complexity in the network layer, and for the datagram subnet, the complexity is in transport layer here. So these were the 6 differences that we had discussed about it. Now we'll go ahead with the routing here. That is routing. In the routing here, that what are the goals needed in achieving a good routing algorithm, that we have to discuss, and even though that has been asked of 10 marks as well. So the goals needed in achieving a good routing algorithm here, the first is that is optimality. In the optimality refers to the ability of the routing algorithm to select the best route. The best route depends on the matrix and a metric weighting that is used to make the calculation. For example, one routing algorithm might use number of hops and delay, but might weight delay more heavily in the calculation. Naturally, routing protocol must strictly define their metric calculation algorithm as well. The second we have here is that is simplicity and a low overhead. simplicity and a low overhead here in this, that the routing algorithm are also designed to be as simple as possible. In the other world, the routing algorithm must offer its functionality efficiently with a minimum of on software and utilization overhead. Efficiency is particularly important when the software implementation, the routing algorithm must run on a computer with a limited physical resource here. We'll go ahead with the third one here. So the third we have here, the third we have is here, that is robustness and stability. In the robustness and stability, that the routing algorithm must be robust. In the other world, they should perform correctly in the face of unusual or unforeseen circumstances such as hardware failure, high load condition, and incorrect implementation. Because routers are located at a network, junctions point, and they can cause considerably problems when they fail. So the best routing algorithm are often those that have withstood the test of the time and the process stable under the variety of a network condition as well. So the next we have here is your, that is your fourth one, that is rapid convergence. In the rapid conversions here, that is the routing algorithm must converge rapidly, and convergence is the process of agreement by all routers and on optimal routes as well. And when a network event causes the routes to either of to go down or become available, the routers distribute routing update message, and routing update message permits that network simulations recalculations of the optimal routers, and eventually causing all the routers to agree on these routes and routing algorithm that converges slowly, that can cause routing loops or network outages as well. Now we'll discuss the another one, that is your fifth one, that is your the flexibility. So in the case of the flexibility, if I'm talking about here, and that is the routing algorithm that should always be flexible. In other words, the routing algorithm should quickly and accurately adapt to a variety of the network circumstances. For example, assume that a network segment has gone down, and many routing algorithms, on being aware of this that has gone down, and aware of this problem, will quickly select the next best path for all the routes normally using the segment. And the routing algorithm that can be programmed to adapt to changes in the network bandwidth, router queue size, network delay, and of course the other variable. Now we'll discuss the difference between the adaptive and non-adaptive routing here. Now we'll discuss about the difference between adaptive routing algorithm, and that is we can say that with this, that is known as the static routing as well, and dynamic routing, which is termed as adaptive routing algorithm as well. So we'll discuss about the adaptive and non-adaptive routing algorithm, or static routing or dynamic routing, that they can ask you either of the name, you have to answer it out. So we'll discuss more than the 6 points here. So here in the case, the first difference for the static routing, that the static routing manually set up the optimal paths between the source and the destination computer. And for the routing, that for the dynamic routing or adaptive routing here, that is the dynamic routing uses the dynamic protocol to update the routing table, and to find the optimal path between the source and the destination computers as well. For the static here, that is the routers that uses the static routing algorithm do not have any controlling mechanism if any faults in the routing paths here. For the dynamic routing here, that the dynamic routing algorithm are used in the dynamic routers, and these routers can sense a faulty router in the network as well. The third difference is between the static and the dynamic here. The third difference for the static here, that is these routers do not sense the faulty computers encountered and while finding the path between the two computers or the routers in the network. And for the dynamic here, that is we have here that the dynamic routers eliminate the faulty router and finds out the another possible optimal path from the source to the destination. The fourth differences between the static and a dynamic routing here. For the static here, that is in the case that the fourth difference, that the static router is suitable for very small network and they cannot be used in a large network. And for the dynamic routing is used for the larger network here. For the fifth differences, the static routing is the simplest way of routing the data packets from the source to destination in the network. And for the dynamic here, the dynamic routing uses the complex algorithm for routing the data packets. For the sixth differences, that the static routing has the advantages that it requires a minimal memory, and for the dynamic here, that dynamic routers have quite a few memory overheads depending on the routing algorithm that is used. And the seventh and the last difference that we have to talk about, and that is the network administrator finds out the optimal path and makes the changes in the routing table in the case of the static routing. And for the dynamic routing algorithm, the algorithm and the protocol is responsible for routing the packets and making the changes accordingly in the routing table here. Let's go ahead with the another one that what we have to discuss here. Explain routing and routed protocols. Routing and routed protocols. So in the case of the routing and the routing protocols here, a host or a router has a routing table with an entry for each destination or a combination of destination to the route IP address routing table that can be either static or dynamic. And a static routing table contains the information entered manually, and the administrator enters the route for each destination into the table as well. The dynamic routing table is updated periodically by using one of the dynamic routing protocols such as RIP, OSPF or BGP. And with that, the routing algorithm that can be classified in the several ways that is based on the representative. It can be classified into two types. That is, the first type we have here is that is a static routing algorithm. The second is dynamic routing algorithm. In the static routing algorithm and the dynamic routing algorithm, we had discussed about the differences here as well. But in short, I will tell you that in the static routing algorithm, that the network topology determines the initial path and that pre-calculated paths are then loaded to the routing table and are fixed for the longer period. For the dynamic routing algorithm change their routing decisions if there is change in topology, traffic, and then each router continuously checks the network status by communicating with neighbors, and thus a change in the network topology is eventually propagated to all the routers. That is based on the informed gather. Each router computes a suitable path to its destination as well here. Okay, so in the same case, if I'm talking about where related to the static and dynamic routing algorithm here, in the same case, if we deal with it, that is another thing that we have to discuss is your Unicast routing protocol. So let's go ahead. So here we'll go ahead with another one, that is your Unicast routing protocol. The Unicast routing protocol, that what we have to discuss as well. In the same case, this has been asked in the many time in the examination paper, so which is very important as well in the same while. Now for the Unicast, that is they had asked you about what is meant by the Unicast and multicast routing with a suitable data that is diagram. We have to discuss about it. So Unicast and the multicast, first we'll discuss about the Unicast routing protocol here. So in the Unicast routing protocol, where that the Unicast with a Unicast design application that can send one that copy of each packet to each member of the multicast group. This technique is simple to implement, but it has significant scaling restrictions. If the group is large, In addition, that it requires the extra bandwidth because the same information has to be carried multiple times, even on shared links as well. But in the multicast routing, delivering a packet sent from a source node to the subnet of the other node in the network here. So now we'll discuss unicast in a detail. In the unicast, that the protocols involve just one sender and one receiver and are often referred to as a unicast protocol, and there is one source and one destination as well. So here with these that is a process like it has a system. This is S1, and it has that is message, that is your S1 D1. It will goes towards it. Then other than that, this S1 D1 that goes towards the direction here, and here it is. Where it goes towards it, and then it moves towards as well, where it will travel S1 D1 in the same direction. Then other than that, it will travel S1 D1, then it will same travel S1 D1 in the same direction, and it will goes to the G1 here. So this is unicasting. And now in unicasting, a unicast packet starts from the source S1 and that passes through the reach destination D1 here. And in unicasting, when a router receives a packet, it forwards the packet through may discard the packet if it is cannot be find the destination address, and it is routing on as its a routing table here. Now we'll talk about the multicasting. In a multicast, there is one source and a group of destination. The relationship is one to many. So here in the multicasting, what it happens that when there are many systems, so it will go like this is the one system. Here it is. Then of course here it is. Then of course here it is. Then of course here it is. And then of course here it is. Okay, so it will travel like this. It will go here. That is it if it's sent as your same message, that is S1 D1. So it first go towards here to here, and that it is sent more over here with one block, then S1 D1, and then it will go, that is S1 D1, and it will receive to the receiver. Next it will move like it will receive to this, that is the same message S1 D1. Then here it is S1 D1. It was received by this message to this one. Next it will move like that is your S1 D1, and then it will get go to this as well in the same direction. Then other than that, it will goes towards there as well. And then it will goes towards as well. Then it will goes towards as well. And same for that, it will passing from one direction to the another, and here it will be as well. This is what it called as that is multicasting here. Okay, in this the multicasting, that the source address is a unicast address, but the destination address is a group address which defines one or more destinations. In the multicasting, when a router receives a packet, it may forward it at and through the several of its interfaces, and the multicasting starts with one single packet from the source that is duplicated by the router, and the destination address in each packet is the same as for the duplication here. Let's go ahead with another in the detail here, that is you discuss the problem of the count to the infinity associated with the distance vector routing technique, because that has been asked of 10 marks. Now we'll go ahead. Problem of count to infinity associated with distance vector routing technique. So in this has been asked of 10 marks here, that an image network and that denotes the distance from the router A to every other router. Until now everything works on fine. Suppose that the link A and B is broken. If I'm drawing a diagram, then we'll discuss this, because that then of course you will be clear about it. So here this is that this is A node, this is B, C, and this is D. And for that we have routing table for A, and for here that is B, C, D. We are drawing for the table A now, so that we'll skip that. So 1, 2, 3. Let's go ahead with another one, that is we have this is sort of a dotted line. This is A, B, C, D. And for this, if I'm drawing the routing table here, and for the same case, so for the BCD, we have 3, 2, 3. Then for the another one, BC, D, we have 3, 4, 3. And for the another one we have here, that is B, C, D, that is 5, 4, 5. So here in this now I think you will be understood about it, that that suppose that the link A and B that is broken, the router B observes it, and but it in this routing table he sees that router C has a route of to A with 2 hops, and the problem is that B does not know that C has a router B as a successor of his routing table on the route to A, and that followed count to infinity problem, and router B actualizes his routing table and takes the router to A and over router C as well. With this particular figure, that we can see that the new distances to A in the router C is routing to the router to A, and that contains the router B as the next hop router. So if B has increased his cost to A, C is forced to do, and the router C increases to the cost to A and about B plus 1, that is which we had equals to 4 here. In the same case, now we see that the consequences of the distributed Ballman-Ford protocol, because the router B takes the path over the C to A, and he that reactualizes his routing table and so on. So there are the several partial solutions to the count to infinity problem, and the first one is to use some relatively small number in the approximation of infinity. For example, we might decide that the maximum number of the hops to get across a certain network is never going to be more than a 16, and so we could pick 16 as the value as represented infinity, and this is the least bound the amount of the time that it takes to count to infinity. And of course, it could also present a problem if our network grew to the point where some nodes were separated by more than 16 hops. One technique to improve the time to stabilize the routing is called the split horizon, and the split horizon technique implies that the routing information about some network stored in the routing table of a specific router is never sent to the routing from which it was received. Now we'll discuss about the issues with the distance vector routing. Issues with distance vector routing. So issues with the distance vector routing here, that the primary drawback of this algorithm is its vulnerability to the count to infinity problem, and there have been proposed many partial solutions with that partial solution, but none works under all circumstances. With this, another drawback of this scheme is that it does not take any into the account link bandwidth, and yes, yet another problem with this algorithm is that it takes an appreciably long time for the convergence as the network size grows, and a fallout of the count to infinity issues and slow conversions has been to limit the maximum number of the hops to 15, and which means more than 16 routers subnet, it may not be appropriate routing algorithm. Now we'll discuss what is unicast routing and discuss the unicast routing protocol, as we had discussed about it, and you know very well that we just I let you gone through with that, that in the unicast routing, that the distance vector routing algorithm is a dynamic routing algorithm, and it was designed mainly for a small network topologies, and the distance vector routing algorithm is sometimes that is called by the other name as well, and in the same case, most commonly the distributed that has been used here, and that more commonly are the distributed Bellman's-Ford routing algorithm, and the Ford-Fulkerson's algorithm is used. So here in the same case, that the term distance vector derives from the fact that the protocol includes its routing update with a vector of the distances or a hop count. In this algorithm, each router maintains a routing table indexed by and containing one entry for each router is in the subnet, and this entry contains two parts. The first is that the preferred outgoing line to use for the destination, and an estimate time or a distance to that destination as well. The metric used might be the number of the hops, time delay in the milliseconds, and the total number of the packet that queued along the path, etc. Assume that the delay is used as a metric, and that the router knows the delay to each its neighbor, and all nodes exchange informations only with their neighboring nodes, and nodes participating in the same local network are considered neighboring nodes as well. Once every tm seconds, that each router sends to the each neighbor and a list of its estimated delay to each destination. It also receives a similar list from each neighbors here. By performing the calculation for each neighbor, the router can find out which estimate seems that the best, and they use that estimate and the corresponding line in its new routing table. An old routing table is not used in the calculation as well. And now we'll go ahead the subnet with the 12 routers here. Here we'll go ahead with the subnet, and that we have a destination as well. So here it is A, this is B, this is C, and this is D here. From A to E we have, and from E to 1, that is I. Then we have same for the references towards it. from B to G it will go out. I will just name it out: A, B, C, D, E, F, G, H, I, J, K, L. So this is all D, H, I, J, K, and then L we have. From this is C to E, and then of course from A to J, and from J to H here. Okay, this is an H boundary, and this is a subnet. This is known as subnet here. And in this there are the 12 routers here. Okay, so this is 1 2 3 4 5 6 7 8 and 9 10 11 12. So these were the 12 routers and that are connected to one another. Now for that, if I'm talking about the JK delay, and that is the JI delay, and for this if I'm talking about कि JK में कितना डिले है आपका एंड JI में कितना डिले है, विद द सेम रिक्वेंस अगर वो इसके थ्रू है कि फ्रॉम A to A है तो ऑफकोर्स वो 0 है, बट A to B है तो दैट इज़ योर 12 ईयर, बिकॉज A to B वो आपका 12 जाएगा, एंड फॉर दैट सेम केस C है, D है, तो वो अपना अपना मूव करता जाएगा. And the maximum for that we have approximately 40 from A to D, or you can say that from D to A here, that is 40, and the terms around it I will just make it out, and so that you will be having a cleared concept regarding that. So here we have the first, that is from to A. This is for A. This is we named as A, B, C, D, E, F, G, H, then I, J, K, and L. We have L routers, so we'll go ahead here. This is for A. Okay, now for the another one we will be having for I, then we have for H, then we have for K, and for the new estimates we have another 2 lines, so you'll go ahead here. It will we have to draw that the number of the routers, and that we have to draw here. It's gonna be like that number of routers with a representation, and then that we have to draw it. Okay, and for that here we have this, as I told you, name it, and this is for new estimated delay from J, and this is line, and from here that is for this, that is your JA delay is 8, JI delay is 10, and JH delay is 12. I will be representing that, and then you will get to know how it will find it out. JK is your 6. From that is new routing table for J, and from here that from starting, this is your 0 12, with this that is your 0 12, then we have 25, then of course we have 40, then 14, then 23, then we have 18, 17, 21, 9, then 24, and then 29 as well. For the I here in the reference towards A, that is 24, B 36, that is 18, 27, 7, then 20, that is 31, then 20, 0, then 11, 22, and 33. Now for the H1 in the reference towards A, that is we have is 20, 31, 19, 8, 30, 19, 8, 0, 14, 7, 22, 9 here. For the K1 here that we have is 21, 28, 36, 24, 22, 40, then we have 31, 18, then we have 22, 10, 0, and 9. For the same case, the new estimation here, this is 8A, the line, and 20A, that is 28I, then of course the 20 after the 28, that is 20, that is H, 17I, and then we have 30I, then we have 18H, then 12H, 10I, 0, that is not of course, and that is 8, that is your K, that is 6 for K, and that is 15, that is K. This is new routing table from the J here, and in the same references, if I'm talking about here in the terms of it, that what we have to deal it, that is in the reference towards this and towards this K, that is the vectors received from J's 4 neighbor. Okay, so this is all about. Now we'll discuss about the Internet Control Protocol. In the Internet Control Protocol, we will have to go through with the diagram first, then we'll discuss the ARP operation as well. That in the Internet control protocol, what they can ask you is you explain ARP, and then of course that is ARP, and what is ARP cache. So in the same case, ARP stands for Address Resolution Protocol, or we can say that RARP, that is stands for reverse ARP. So that is the ARP cache here. So in the terms of ARP here, that it stands for that ARP associates an IP addresses with its physical address, and anytime a host or a router needs to find the physical address of the another host or the router on its network, and it sends an ARP query packet, that the packet includes the physical addresses and the IP addresses of the sender and the IP addresses of the receiver as well. In the same case here, now we will go ahead with the detail, and that what we have to discuss here in the same here with the reference towards that the operation of ARP here. In the reference towards the ARP, that is your address resolution protocol, here the ARP associates an IP addresses with its physical addresses as well. And in the same way, that anytime a host or a router needs to find a physical address of another host or router on its network, it sends an ARP query packet, and the packet includes that the physical address and the IP address of the sender and the IP address of that particular receiver here as well. Now we'll discuss about the operation of ARP, that what we have to discuss here. And for that we have this is a system A which requests system B. Of B system, we have an IP address 158.108.2.4, and for IP address of system A, we have 158.108.2.2. and then after that, other than the request, we have here that is your system C. Then we have here as well that is your system D. And then of course we have your system E. We are this having a system of 158.108.2.3, and here it is that is 158.108.2.5 here. So this is a broadcast request. In the broadcast request here, we have to discuss about it, and then other than that, with this system that are interconnected to one another. And even though there are another series that is 15.81, that is a unicast reply, like that they reply and they request it, and for that particular from one system to another system, and that are connected to the another one, that is unicast reply one-on-one here. That is the another way. And consider the following example, like computer A and a computer B that shares a physical network, and each computer has an assigned IP address of I and IB, a physical address of P or PB. The goal is to devise that a low-level software that hides a physical address and that allow high-level program to work only with the internet addresses. And the addresses mapping must be performed at each step along the path from the original source and the destination. And even though the sender must map the intermediate router internet addresses to a physical address, and the problem of mapping high-level address to a physical addresses is known as the address resolution problem, and has been solved in the several ways. Like physical addresses are of two types, and that is your physical address of two types that we have, and where it stands for in the form of, like, there are two types. The first we have Ethernet, the second is Pronet. So in the same case, these were the two physical address types here. Let's go ahead with the another one, and that what we have to discuss. In the Ethernet has a large and a fixed physical address, and Pronet has a small, easily configured physical address. And the address resolution is difficult for the Ethernet, like in networks, but easy for the network like Pronet. ARP allows to the host to find the physical address of the target host on the same physical network, given only the target's IP addresses as well. In the same case, if I am talking about this, that shows the host A broadcast and ARP requested that continuing to the that is IP to all the computer on the network, and if this the another one that reply towards it, that shows the B respond toward the ARP replay, and that consists that the pair of IB or PB, that to reduce to communication cost, the ARP maintain a cache of recently acquired IP, so physical address binding, and so they do not have to use ARP repeatedly. Whenever the computer receives an ARP reply, that it saves the sender's IP addresses and corresponding hardware addresses in its cache for the successive lookups. And when transmitting a packet, a computer always look in its cache for the binding before sending an ARP request as well. If a computer finds the desired binding in its ARP cache, it needs not broadcast on the network, and when ARP messages travels from one computer to another, they must be carried in the physical frame as well. Let's go ahead with another one, that is the reverse address resolution protocol. Reverse address resolution protocol. So reverse address resolution protocol here, in some situation a host may know its MAC address but not its IP addresses. For example, when a diskless computer such as an X terminal is being bootstrapped, it can read the MAC address from its Ethernet card, and its IP address is usually kept separately in a disk at a server. And the problem of the getting an IP address from a MAC address that can be handled by the RAPs, and which works in a fashion similar to the ARP here as well. In the same case, what we say that the operations of RAP here, what it stands for, they are the system that are connected to one another, and that is known as the RAP protocol here. Let's go ahead here. This is a system A, this is system B, this is system C, and this is system D. For that, they are connected to one another here, and for here that is connected to one another. This is a RAP protocol here. Now we'll discuss related to the RAP protocol that the sender broadcasts a RAP request that specifies itself as both the sender and the target machine, and that supplies its physical addresses in the target hardware field, hardware address field as well. And all the machines on the network that receives a request, but only those authorized to supply the RAP services process that the request and the send a reply as well, and such machines are known as a RAP server. And for the RAP success, that the network must contain the at least one RAP server here. Like an ARP message, a RAP message is sent from one machine to the another, encapsulated in data portions of network frame, and an Ethernet frame that carrying a RAP's request has the usual programmable Ethernet source and the destination address, and the packet type field in a float front of the frame as well. And the ARP cache is a collection of ARP entries, mostly dynamic, and that are created when the host name is received to an IP address, and then IP address is resolved to a MAC address as well. In the same case, we say that there are the two different ways that cache entries can be put into the ARP cache, and that what we have here is that we have here, the first we have is your, that is static ARP cache entries, and the second we have here is your dynamic ARP cache entries. So these were the two, static ARP cache entries and the dynamic ARP cache entries as well. In the static ARP cache entries, that these are the addresses resolution that are manually added to a cache table for a device and are kept in the cache on a permanent basis. Static entries are typically managed using a tool such as ARP software utility. And for the dynamic ARP cache entries, that here these are the hardware IP addresses pair that are added to a cache by the software itself, and as a result of the successfully completed past ARP resolution, they are kept in the cache only for a period of time and are then removed as well. Now we'll discuss about the advantages of ICMP, where they can ask you what are the advantages of ICMP over IP protocol, and explain the ICMP with the general frame format. So let's discuss about it. The advantages of ICMP over IP protocol. Here there are the three advantages. The first is that the ICMP protocol helps network administrator by assisting them in a diagnosis networking issue. And the second advantage is that ICMP have over IPA protocol, that ICMP allows the gateways to send error or control message to the other gateways or host. The third advantage is we have that ICMP messages are used to obtain the time from the another machine. Let's go ahead with another one, that is in the respect towards it, that is ICMP general frame format. So ICMP general frame format here, in this, that shows the basic error message format, and ICMP messages is encapsulated into the data field, where in the same case in that data field and that an IP packet and an ICP header is 8 bytes long and a variable size data section as well. So here we'll go ahead with this. This is 0, 8, 16, 31. This is type. This is error message format. In this, the first we have is your type 0 to 8. The second is code. The third is checksum. This is reset of the header, and this is IP header and 64 bits of original datagram. In the same case here, the type stands for, it is an 8-bit field, identifies that the type of a message, where the code is that the size of the code is field is 8-bit, that from 8 to 16, and it provides the information as a parameter of the message type, where the checksum, this is a 16-bit field, is used to detect the error in the ICMP message, where the IP header plus the original datagrams that we have here, that is that the field that can use the diagnosis purposes by matching the in the information and the ICMP message with the original data in the IP packet as well. Now we'll discuss about that the give a general format of ICMP, where the general format we'll discuss here, that is your general format of ICMP, and explain the different errors reporting message used in that is in ICMP, that we will discuss as well. And in the same case we have here that the general format of ICMP we had discussed in we had discussed here, and in the same case we will discussing about the different types of the error that is reporting in the message here. Different types of error reporting message. This is here that ICMP handles the 5 types of error. The first type of error we have here is here, that is destination unreachable. In the destination unreachable here, the ICMP destination unreachable message is sent by the router in response to the packet, and which it cannot forward because that the destination in the same reference to the destination or the next hop is unreachable, or as the services is unavailable. And a big example of such cases include a message address to the host which is not there and therefore does not respond to the ARP request, and message addresses to the network prefix and for which the router has no valid route as well. The second we have is your, that is source quench. Source quench, that is a machine use ICMP source quench message to report congestions to the original source, and a source quench message is a request for the source to reduce its current rate of the datagram transmission. No ICMP message to reverse source quench message, and source after receiving a quench message reduce their transmission rate and then gradually increase their rate provided no additional quench message are received. The third we have here is your, that is time exceeded. In the time exceeded here, that is your that is every IP datagram that contains a field that called here, that is your time to live, and or the TTL, and on each hop along the path of the destination the TTL field is decremented by 1, and when the value of the TTL field equals to 0, the datagram is discarded to prevent the datagram from floating around the network forever, and the gateway that may always also notify the source host why the time exceeded the message here. Now we'll talk about the next one, that is the fourth one, that is the parameter problems. The parameter problems here, that is if the gateway or the host processing a datagram finds a problem with the header parameter such as it cannot complete the processing the datagram, it must discard the data graph, and where that the one potential source of such problem is with the incorrect argument in an option, and the gateway or the host may also notify the source host and why the parameters problem message as well, and this message is only sent if the error caused the datagram to be discarded. The next we have is the fifth one and the last one as well, that is your redirection. In the redirection here, that ICMP redirect message that can only be sent by the routers here. So these were the different types of errors reporting message here. Let's go ahead with a question that has been asked of 10 marks and which is very important towards it, and that is the congestions control. The topic related to that is your congestion control. Now in the congestion control, the question is, what is the transmission time of the packet sent by the station if the length of the packet is 2 million bytes and the bandwidth of the channel is 300 kbps? This has been asked of 10 marks. So let's go ahead. What is the transmission time of a packet sent by a station if the length of the packet is 2 million bytes and the bandwidth of the channel is 300 kbps. So this has been asked of 10 marks, which is very important towards towards the exam, that what they had asked you, because 10 marks बहुत होते हैं. And for that we have a solution here. In that the packet size is 2 million bytes, so that will convert it to 2, 3, 4, 5, 6 zeros, multiply with 8 bits because packet size 8 bit tha. And for the bandwidth is equals to 300 kbps, which is equals to 3, 1, 2, 3, 4, 5 zeros bps. And then the transition time equals to, that is your packet size that upon bandwidth. So packet size upon bandwidth we have 2, 1, 2, 3, 4, 5, 6 zeros multiply 8 bits upon 1 2 3 4 5 5 zeros bps. When we cancel it out, first we'll multiply 8 to the 16, so it will be 16 and 6 zeros upon and 3 5 zeros. Then we'll cancel it out, and you will cancel it out 3 4 5 5 zeros from here, and then 160 divided by 3, so we'll get 53.33 seconds. That is your transition time. That will be the answer here. So this has been asked of, that is of 10 marks, which is very important at last for your competition for your university exams here. And now we'll discuss more over the topic here, that what we have to discuss as well, and that is the another topic in the reference towards it. Like when we'll go ahead with the congestions here. So here that the question can be arise of 10 marks, that is the reasons for congestions in the network. Reasons for congestions in a network. And we have to even to explain that any one method congestions in the control, that has been asked of 10 marks as well. In the same reference towards it, that is, if I'm talking about, then we will go ahead, and that is 10 marks question paper, and that is the reasons for the congestions in a network. The first reason is that the main cause of the congestion is slow processor speed, and if the router's CPU speed is slow and performing the task like queuing, buffers and table updating, etc., so the queues are built even though the line capacity is not fully utilized. And that is the second is that the bandwidth of the link is also important in congestion, and the links to be used that must be high bandwidth to avoid the congestion as well. The third reason we have here is that is any mismatch between parts of the system that also cause the congestions of the grading of the processor speed but not changing the link, and the vice versa will cause the congestions. And the fourth reason we have that when the arrival of the packet are not uniform, that is when the traffic is bursty. So these were the things, and now we'll go ahead with more detail related to the congestions and the leaky packet and the total bucket as well. So that will go in the cover up in the next coming class. So thank you, hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion on the comment box. Please like, share and subscribe our channel, so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. And in the computer network, if I'm talking about, what we had cover up is that is in the same case we had cover up the unit 1 here. And in the unit 1, that is your introduction concept, and that is we had cover up about the goals and application of network structure and architecture, the OSI reference model, the services, network topology design, delay analysis, backbone design, local area network design, and that is physical level transmission, media switching, media ISD and terminal handling. And then medium access sublayer में medium access sublayer, channel allocations, LAN protocol, Aloha protocol, overview of IEEE standard, FDDI, data link layer, elementary data link layer, sliding window protocol, error handling. In the unit third is your network layer, that is a network layer, point-to-point network, routing, congestions control, inter-networking, TCP IP, IP packets, IP address, IPv6. In unit 4, transport layer, that is your transport layer, design issues, congestions management, sessions layer, design issues, remote procedure call, presentation layer, design issues, data compression technique, cryptography, and TCP IP window management. And in the unit 5, that is application layer, file transfer access and management, electronic mail, virtual terminals, other application, examples network like internet and a public network. That what we have to cover up in the next coming classes. So class आज के लिए इतना ही. Thank you. Hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion on a comment box. Please like, share and subscribe our channel. Thank you.